want to thank the organizer for the kind invitation. I have the very fond memories of these meetings. I have been attending this meeting for 10 years, and I'm very much looking forward to see everybody in person again, maybe at the next one. So today I'm going to talk about new examples of translating solitons in Minkowski space. So this is joint work with Miguel Ortega from the University of Granada. And we started this work in 2017, I believe, when he visited me for the first time in London. So first of all, maybe for the younger people in the audience, I'm going to remind you very quickly of what the mean curvature is. So in the case of a surface in R3, what we want is a good notion of curvature for a surface, and the notion we know is the notion of the curvature of a curve. So of course we have that on the surface in R3 because it's embedded in R3. So what we can do is take a normal section and cut the surface, and this defines a unique planar curve which is given by the normal section when it cuts the surface, and we can take the curvature of this planar curve. But of course, we have many normal sections we can take at a particular point. So what we're going to do is that we are going to take all these normal sections with all the planar curves defined by the normal sections. We're going to take the biggest curvature, which is called, and the smallest curvature, which are called the principal curvatures. We're going to take the average. And the average of these two principal curvatures is the mean curvature vector. So this defines a vector field at each point in the direction normal to the surface. This can be generalized to higher dimension for immersions in of a manifold with a connection into an arbitrary ambient manifold of any codimension. And the way we define the mean curvature in this case is just we take the second fundamental form, which is basically the normal part of the connection, of the big connection of the ambient connection, and we take the trace, and the trace is the mean curvature. And it can be shown that these two definitions coincide. Oops. So now I'm going to define, because that's the purpose of this talk, what this mean curvature flow is. So as I said, we have a mean curvature field which is defined at any point on the surface, and this field is normal to the surface. So of course, since we have a field, we can define a flow, and the idea of the mean curvature flow is just to deform the surface and let it evolve along this normal flow of the mean curvature. The original case of the mean curvature flow was the ambient space Rn plus 1. So what do we do in that case? We take an orientable hypersurface of Rn plus 1, F0, and we take a smooth family of immersions, Ft, from F cross I, so it's a one parameter family, to Rn plus 1, such that F0 is just the surface for t equals 0. And then we say that Ft is a mean curvature flow if the velocity, the perpendicular direction, the perpendicular part of the velocity vectors coincides to the mean curvature vector at each point, right? And and H is the mean curvature field of the immersion. So intuitively, this flow is also called, in the case of curve shortening flow. Well, why? Because if we imagine a curve, a closed curve in R3, in R2, if we deform it with the mean curvature flow, what we're going to have in finite time is a convex curve, which is going in finite time to blow up, to converge to a point, first to a round circle, and then to a point. So this is why it's called the curve shortening flow. So this particularity of having finite time blow up can also be seen in the general case of convex surfaces. So this is a result which was proved by Husken not too long ago. But of course, this equation here is very difficult to solve in general. So rather what one expects, rather than to solve it, is to find short-term behavior or the existence of solutions of finite time blow up. And in order to be able to say something about that, what one usually does is that one considers special solutions of the mean curvature flows, the solutions that evolve by a group of conformal transformation of the ambient space. And these particular solutions are called solitons. So for example, in the case where the group of conformal transformation are homothéties, then these solutions are called self-shrinker. And in the case where this group here is are the translations, and when one calls it the translating solitons or translators. And these particular solutions are exactly the one we're going to look at today. So for translating solitons in our n+1 in general, what does is that, as I said, so we look at solutions of the mean curvature flows which are invariant or which evolve by a group of translations. So the equation reduces to the following one here. So meaning that the mean curvature is equal to the perpendicular part of a constant fixed vector in Rn+1. And since we're in Rn+1, it doesn't matter which vector we take because Rn+1 is full of symmetries, right? And usually in literature, we fix this vector to be just a vertical direction. So now in order to make our studies a little bit easier, what we're going to look at today are graphical translators. So translating solitons, which can be written as a graph over the horizontal plane. So remember, we're moving in the vertical direction, and we look at graphs over the hyperplane, which is the horizontal hyperplane. So in this case, the surface just becomes a graph of this function for some function from Rn to R. And the family of immersions associated to the graphical translators become a bit easier, meaning that it is just our original surface F0, which is translated, and this is exactly this term TEN+1 in the vertical direction for some function U. In this case, we have a nicer expression in terms of the function U for the translating soliton, which is given here. Well, still, this equation is pretty hard to solve, right? So it becomes elliptic. Now it's elliptic at least, so we have all these elliptic regularity theory we can use, but it's still pretty hard to solve it explicitly or look at behavior of this equation in general. So we do some additional thing. We look at solitons which are invariant under a group of transformation. So for example, those are the solitons which are horizontal by translation. In this case, well, I give two examples of that. These examples of solitons which are invariant by translation in the ambient when the ambient space is Rn+1. So the first example is just a stupid example. It's a plane, right? You can see that it's static as a matter of fact. So it's a minimal case. If you translate in the direction in the horizontal direction v, one loss isn't going to change. You just get the same plane. And the other example is just a Grim Reaper. The Grim Reaper is called the Grim Reaper, which is this curve here. So this is the Grim Reaper curve, the profile curve, and then you take the cylinder over it, and as you can see, if you move it with respect in the vertical direction, while the horizontal direction, the cylinder doesn't change. And as a matter of fact, we can show that in Rn+1, these are the only example up to isometry and maybe tilting the Grim Reaper cylinder of translating soliton, which are invariant by translations. So maybe a little bit more interesting examples are the translating soliton which are invariant by rotational symmetries. So in this case, one can show that actually the only examples where is a translating paraboloid, which is a graphical soliton, or something which is called a wind-like translator, and which is made out. It's not graphical, as you can see, because here it's tangent to the horizontal axis, but it's made of two graphical solitons glued together. And this was a result, I believe, by Clutterbuck, Schulze, and Schnurrer. And so it can be shown that those are the only translating solitons which are rotationally invariant. And one nice thing which I want you to remember is that in this case, the equations becomes a nice ODE. So this complicated equation we had here, in the case of rotationally invariant symmetries, becomes an ODE. actually in the case of horizontal translation as well. And this is something which is an example of a much more general geometric statement, actually, which we're going to discuss later. So, but now we want to quit the ambient space Rn+1, and we ask ourselves if there can be generalization of translating soliton in other ambient manifolds. But of course, in order to do that, we need to have a vector in the direction of which we translate, right? So as I said, in Rn+1, we can just take any vector, it doesn't matter. But in a general ambient space, this is not the case. So the first thing which comes to our mind is a killing vector field, right? And there is a nice work which appeared recently by Lira and Martin, where they look at translating soliton in the direction of killing vector space. But when we thought at it the first time, we just thought at looking at products. So we considered semi-Riemannian manifold N, and we considered the product with R of these semi-Riemannian manifolds. So here, epsilon prime means that we could have either minus or +1, right? So in general, we can consider any semi-Riemannian manifold, but of course, if we want a Lorentzian manifold, we have either here on the G a Riemannian metric, and then the dt has to be the epsilon prime has to be a minus, or we can have a Lorentzian metric G, and then epsilon prime is going to be 1. And in this case of a product, we just looked at dt, which is a nice vector. It's a particular vector in this product. It's killing, it's unique, and it has an integrable orthogonal distribution. So this means that we can consider graphs in the direction of the vertical, so to say, the vertical axis. So we replace our vertical axis by this dt here. And we will call it F a translating solution of the mean curvature flow if the mean curvature is not anymore this perpendicular part of the vector v, but the perpendicular part of this dt, of this special killing vector here, where this is a normal component along F. So again, as I said before, we can construct graph map, where this time the dt replaces our vertical axis, and we can compute what is the equation for this special type of graphical translating soliton. And as a matter of fact, this equation is, in the Riemannian case, it's the same than the previous equation we had in the case of Rn+1. If we look at semi-Riemannian manifold, we have some epsilon here appearing. So these are epsilon prime, as I said before, just a sign of the axis, right, in the product. And the epsilon gives us the causality of the soliton we're going to look at. So this is going to give us, the epsilon is just the norm of the normal vector, which is going to give us what type of solitons we're looking at. But now back to something I have talked a little bit about before. We saw that in the case of rotationally symmetric solitons, our PDE reduced to an ODE. And this is an example of a much more general fact, actually. Let me first give the general results. So we have our manifold M, and we assume that it's a semi-Riemannian submersion over an open interval. So this means that the pre-image of F for any S in the base is an hypersurface in N, and that we have a globally defined unit normal, which is nabla pi, where pi is the projection. And in our context here, we're going to assume that this submersion has constant mean curvature fiber. But this is important because we want to define a fiber mean curvature function, right? So in this case, this is a technical lemma. It's not that important. It's just going to tell us that we're going to be able to replace our complicated partial differential equation by an ODE. So if we have a function f such that u, the graph function of our soliton, is f of the projection, then we have that the mean curvature function is a smooth function satisfying some equation. And basically, so this is a bit technical, don't care too much about it, but inside of our partial differential equation here, we're going to be able to replace everything in terms of this function f on the base. So basically what we have, maybe a commutative diagram, is going to be to give us the intuition we need here. We have our manifold F, we have our manifold M and our translating soliton inside of the product, and we have a submersion here. And then our theorem says that our first result says that if F is a translating soliton upstairs, if and only if this function F here is a solution of a particular ODE. So note that I haven't said that F is a translating soliton downstairs, because this is only the case if the submersion is minimal. So in the case of we have minimal fiber, then we have an equivalence here between a translating soliton upstairs and a translating soliton downstairs. And I want to make a remark that I have restricted myself to the case where we have a submersion onto an interval. But actually, we proved this much more generally for any type of submersion with constant mean curvature fiber. And it means that we don't need an open interval here. It's just that in that case, of course, we won't get an ODE. We'll get a lower dimensional PDE. So why is it nice? Well, it's nice because the particular case of this submersion is when we have a nice Lie group acting by isometry on the manifold, right? In that case, we have a submersion between M and the quotient of M with the action of the group, such that the fibers are orbits of the action. We can show that these submersion are in general submersion with constant mean curvature fiber. And then we have this nice result, and F is a G-invariant translating soliton, if and only if F is a solution of this PDE, of this ODE here. And this is where I want you to remember the rotationally invariant cases, you know, like, I mean, maybe I should go back and show you the equation again. So we have this equation, and now this looks familiar, right? This just means that in the rotationally invariant case, what we are doing is that we are letting SON act by isometry on our manifold, and we get a submersion, and then we can bring back the PDE to the nice ODE. We can, if not solve, you know, look at the behavior. So maybe since I don't have that much time, I am going to just talk very fast about this thing. So, I mean, we looked at this equation, and as I said before, in the rotationally invariant case, we had two types of solution. The ball, which was a graphical, globally defined entire solution, and we had wing-like solutions. Well, we discussed in our paper when we have such a solution here, and we found that in general, we always have, depending on the causality of the solution, balls, like entire graphical solution, and wing-like solutions. And maybe I should, again, since I don't have that much time, pass to something which is maybe a bit easier to understand. Can you see that?
Yes. Yes, yes. Very good. I can see it.
Okay, so this is my general ODE, for an arbitrary submersion when I have a group action. And we are going to look at two examples. So an SON action on Rn minus 0, and this action here of the boost group in the case n equal 1 on a Lorentzian manifold minus a cone. But let me start maybe with the beginning. So here, remember, this epsilon was a sign of the norm of the normal vector. So this is going to give me the causality of the soliton. So if epsilon is equal to -1, I have a space-like soliton. If epsilon is equal to 1, I have a time-like soliton. So now let's look at the first example. Our first example was just to take Rn with definite metric, and make a Lorentzian product out of it, meaning that the epsilon prime here was -1. So I have this metric here. And we look at the SON action on Rn minus 0. So why? Well, because, I mean, we want to have a nice Riemannian submersion, right? So we want our quotient to be Hausdorff. And if we have the 0, this is clearly not. So we have to take the 0 out. And in this case, so this is a picture of the action of the group in the case n equals 2. The orbit space is just the interval 0, infinity here, and it is Riemannian. So meaning that epsilon tilde here is going to be 1. our only equation here reduced to this equation, and basically what we did, which was a lot of work, but it was analysis basically. We looked at the behavior of these solutions, and here is what we got. So the first thing we notice is that plus minus 1 is the light-like solution here. So if we consider solutions, we're going to be either between -1 and 1 or above and below, right? So in the case that we have a space-like soliton, so in the case where we have epsilon equal -1, well, we need this here to be negative. So we need f prime square to be smaller than 1. So what it means that in the case of a space-like soliton, we are between -1 and 1 here. And here, if you look at the equation, again, this is an equation which depends only on the derivative of f prime, right? So we can just set w equal to f prime and look at the solution of, at the behavior of w. And what we found is that we got 3 solutions in this case. So the ball, which is the only entire solution, and 2 families, so the Yukai and the Calyx family. So Miguel found this name, which I think are really cute. So one is a family above the ball with critical points, and the other one is below the ball. So I'm going to show you another picture in a bit. Below the ball with no critical points, right? And so so these are the 3 solutions, the 3 possible solutions we get in the case of space-like solitons. And in the case of time-like solitons, we have to have that f prime squared is bigger than 1. So we get 4 solutions. We get 1 finite type blow-up solution in the case where we are here, where f prime is smaller than 1. And again, we get 3 solutions. The time-like ball above, which is a unique entire solution, and 2 families of solution, a family which is below the ball, which is globally defined and has critical points, and a family which is above the ball with finite type blow-up. So we have 4 solutions, I said, but actually we have only 3, because these 2 solutions we can glue together. I'm going to explain that in a bit. And the second example we looked at was the Lorentzian space, so with Lorentzian matrix ds squared, and we took the Lorentzian product. So this time the dt had to have was positive definite, right? Our epsilon prime was equal to 1, and then we looked at an SN-1 action on. So again, we want a nice pseudo-Riemannian submersion, so we have to make the quotient by the group Ostov, right? So we have to take out the cone. The 2 lines of the cones and the 0. So what we get here when we look at the submersion, the orbit space are just these 4 axes here, these 4 0 infinity interval, and we can restrict to each of these intervals basically. So we in the nice case of a submersion onto an interval again. And this time we have to differentiate between 2 cases: the Riemannian case, where we restrict the action to the Riemannian submersion here. So this is the S, the yellow part, and here the submersion is Riemannian. So what we get is these equation here. And we have another possibility. Well, if we restrict to the case where the submersion is Lorentzian, so we look at time-like vector here, and a submersion, of course, the epsilon tilde is going to be -1, and we have this equation here, right? So now we can look again at the causality of solitons. So in each of these 2 cases, we have either that the soliton is space-like or that it is time-like. Well, in the case where the submersion is Riemannian, we can't have a space-like soliton because 1 plus f prime square is always bigger than 0, right? So we cannot have epsilon equal -1. In the case where the soliton is time-like, we have 2 solutions, and this is not a surprise because you should recognize this equation. This is basically the equation, the same equation we had for the Riemannian case, which was done by Clutterbuck, Schluck, and Schnürer. This is the rotationally invariant case. In the Riemannian case, this is the same equation. So we get again the 2 solutions, the ball and the wind-like solution.
Sorry, Marie-Amélie, maybe 2 or 3 more minutes,
Okay.
just as a warning.
Yeah, so I'll wrap up very quickly. So this
Very
is
good.
the second equation, and basically this equation we can, it's the same equation than the one we have in this case. It's just reversed. So we get exactly the same type of solution here, but it's time-like. And the very interesting property of the solitons here is that we get hybrid solitons. So we can actually glue the entire translating solitons of these two types here together, and those are the only entire translated solitons. So let me just show you a few pictures. So this is for example, the space-like case where you have this is the bowl solution, and this is the two families, the one with the critical points and entire solutions, and this is the one below. So I had also the time-like solutions, but I have no time. And these are the space-like examples and the time-like examples in the first case, in the SON invariant case. So as I said, so with the function we are looking at is f prime, right? So we have to integrate, and then in order to get our surfaces in R3 to rotate with the group SO in order to get the surface. And I'll stop here then.